Welcome back to Calculus 3. I'm Dr. Jeff Groh, and today we're going to talk about curvature, torsion, and Frenet frames. We begin, as we always do, with some definitions. The first one we've already defined. The unit tangent vector to a curve R of t is, we'll denote it by a capital T, and it's defined to be the normalization of the velocity vector, i.e. r dot over the norm of r dot. That way, if you have some curve, the unit tangent vector always is tangent to this curve and of length 1. Let's do a couple quick examples. Let's suppose r of t is, let's say, r cosine omega t, r sine omega t. As you can see, the velocity vector will be negative omega r sine omega t, positive omega r cosine omega t. To calculate the norm, it might be easiest to factor out the omega r, because what's left over has norm 1. If we assume that both omega and r are positive, then the norm is omega r. The unit tangent vector then, which is the velocity vector divided by the norm of the velocity vector, the normalized velocity vector, will be what you get when you divide this omega r off, and you get minus sine omega t positive cosine omega t, which obviously has norm 1. Let me emphasize, the norm of the unit tangent vector is 1. For another quick example, let's suppose r of t is equal to t squared, and I want to find the unit tangent vector at t equals 1. Here's what we'll do. We'll find the velocity vector. By the way, if x is t and y is t squared, that means y equals x squared. We're looking at a parabola being swept out from left to right. The velocity vector will be 1, 2t, and the velocity vector at 1 is going to be 1, 2. The norm of the velocity vector is the square root of 5 then. Square the coordinates, add them up, and take the square root. The unit tangent vector at 1 then is going to be the vector v divided by the norm. That's going to be 1 over the square root of 5, 2 over the square root of 5. Let's find the tangent line to the vector valued function, let's say cosine of t sine of t at t equals, let's say, pi over 2. To do this, we'll find the velocity vector, which is tangent to the curve. That's going to be minus sine of t cosine of t1. If we evaluate that at pi over 2, we'll get minus 1, 0, 1. The equation of the tangent line is some point on the curve plus t times v. A point on the curve at t equals pi over 2 will be 0, 1, pi over 2, minus 1 times t, 1. All right, r of pi over 2 is 0, 1, pi over 2. We'll have 1 plus 0t, and then pi over 2 plus 1 times t. And this gives you a parametric form for the equation of the tangent line. Recall that the norm of any vector squared is the dot product of the vector with itself. In particular, if I look at the norm squared of the unit tangent vector, I get 1, but that's also t dotted with t. What I'm going to do is take the derivative on both sides with respect to the parameter t. On the right-hand side, we have to use a Leibniz rule. That gives you the derivative of the first times the second plus the first times the derivative of the second. Make sure to use a conspicuous dot. So it's t dot dot t plus t dot t dot, which is clearly twice t dotted with t dot. Keep in mind this is equal to 0. This too can be canceled off. Two vectors have a dot product equal to 0 if and only if they are orthogonal. So the unit tangent vector is at a right angle to the derivative t dot. Whatever our curve is doing in R3, we'll have the unit tangent vector and the normal vector going this way. There actually is a whole plane of normal vectors. This is going to be related to something called the principal unit normal vector. Now t dot is at a right angle to t, but that doesn't mean it's normalized or has norm 1. So here's what we'll do. The principal unit normal vector n is defined by the following expression. It's t dot divided by the norm of t dot. So in other words, the norm of n is 1, since it's a normalization of t dot. So the principal unit normal vector will lie at a right angle to the unit tangent vector. But there should be one more direction, normal to t. Have you ever seen a framing square? An angle iron? They usually look something like this. Little measuring marks off on each side. It's one way of measuring a right angle when you're putting together some kind of a box or framing something. Basically, you have two directions, and they are at a right angle to each other. Given any other point in the plane, you can figure out a vector that goes to that point by taking a rescaling of the first vector in the frame, and then a rescaling of the second vector in the frame. So if you have a pair of vectors that lie at a right angle, you can reconstruct any other vector in the plane by appropriate rescalings of those two added together. In R3, it takes one more vector to do that. You need a vector here, and another vector poking out in the other direction. Then any vector in space can be reconstructed using this so-called frame. If they all lie at a right angle to each other, if they all have length 1, it's called an orthonormal frame, where the ortho and the normal form a single word in this case. If you have an orthonormal frame in R3, you can reconstruct every other vector in R3 from combinations of those three. That's one reason that R3 is three-dimensional. So far, at each point on some curve, we'll have both the unit tangent vector and some normal vector lying at a right angle to each other. But if we are in R3, at each point on that curve, there should be one more vector that's normal to both t and n. We're going to call that the binormal. The binormal is denoted by a capital B. Now, if you had two vectors, t and n, and you wanted to find a vector that was normal to each, what would you do? Yep, you would take the cross product of t and n. That would certainly be normal to both t and n. Note that the norm of b is equal to the norm of t cross n, which is the norm of t times the norm of n times the sine of the angle theta between t and n. But theta is pi over 2 because these are at a right angle to each other. That means the sine of pi over 2 is 1, the norm of t is 1, the norm of n is 1, the sine of pi over 2 is 1, the norm of the binormal is 1 by design. At each point on a curve, we're going to have an orthonormal frame. We'll have a third vector v. This orthonormal frame will be carried along as you move along the curve, and it will go as follows. T is tangent to the curve. N, we'll have more to say about what direction n points at in a moment, goes off. The binormal will be determined by the plane that contains t and n. It will be normal to that plane, according to the right-hand rule. As an example, let's consider a helix. Let's say 2 cosine t, 2 sine t, t. The velocity vector is going to be -2 sine. I'll save space by writing capital S in place of sine and capital C in place of cosine. 2 cosine and then 1. The norm of that is the square root of your -2 sine squared plus 2 cosine squared plus 1, which ends up being the square root of 5. 2 squared is 4 sine squared plus 4 cosine squared. You can factor the 4 out and get 4 times sine squared plus cosine squared. By the Pythagorean identity, sine squared plus cosine squared is 1. You'll end up with 4 plus 1 is 5 under the square root. That means then, it follows then that t, being v over the norm of v, is 1 over root 5 times -2 sine, 2 cosine, and 1. To find t dot, we'll take the derivative, 1 over root 5, minus 2 cosine, minus 2 sine 0. Now we need to normalize this. It's easiest if we pull the negative 2 out from this vector. What's left over has norm 1. So the norm of t dot is, scalars pull out of norms in absolute value, positive 2 over root 5. It follows then that the principal unit normal vector, which is t dot over norm t dot, by definition, is this vector divided by this scalar. The 2 root 5 will cancel off. We'll just have negative cosine, negative sine 0. Now the binormal is t cross n. I should write the components of t above. I'll write it as 1 over root 5, and then we'll bring and then negative 2 sine, 2 cosine 1. The 1 over root 5 is coming along for the ride. We will have then 0 minus negative sine. That gives you sine. You will have 0 minus negative cosine, but don't forget to put a minus on that middle cofactor. Then we'll have 2 sine squared minus a negative 2 cosine squared. That's 2. It's pretty easy to see that b is orthogonal to both t and n. Taking the dot product with n, you'll have a negative sine cosine and a positive sine cosine and then a 0. You get 0. So b dot n is 0. Also, here we'll have a negative 2 sine squared and a negative 2 cosine squared, which adds up to negative 2, and then a positive 2 when we multiply the last coordinates for a total of 0. So again, b is orthogonal to t. We call this the T in B frame. I will ask you on the exam to find the T in B frame for a given curve. For this particular helix, we have the tangent vector, which is tangent to the curve. The normal vector is always parallel to the xy plane. And the normal vector just is orthogonal to both of those, the binormal, coming off like this. Note that the z-coordinate on the binormal is positive, so it's going to go up in the direction that we're spiraling. Let's suppose we have a plane, and we have a frame on that plane. Let's say u and v form a frame. Some vector w that lies in that plane is said to be in the plane spanned by u and v, because you can rewrite w as a combination of a rescaling of u plus a rescaling of v. So w, if it lies in the plane containing u and v, is said to be in the span of u and v. It can be reconstructed from the vectors u and v alone. I now want to talk about acceleration, given this new context of the T in B frame. This will have something to say about acceleration, believe it or not, and it's something I think you'll want to know. In particular, we have a theorem. The acceleration vector, which is the derivative of v, lies in the plane spanned by t and n. An acceleration vector never has a component pointing in the direction of the binormal. the acceleration vector can always be expressed as a combination of the unit tangent vector and the principal unit normal vector. In other words, the acceleration vector will have some scalar multiple called a sub t of the unit tangent vector plus a scalar multiple times the n, but with no part in the direction of the binormal. This seems like a pretty important and significant statement. We will also want to have formulas for these scalars, and we will derive them. In the proof, I want you to recall the definition of the unit tangent vector. It is the velocity divided by the speed. And that implies that the velocity vector is the speed times the unit tangent vector. From this, we can calculate the acceleration by just calculating the derivative. Now, the speed changes with time. You don't have to be moving at a uniform speed, which means you're going to get the time rate of change of speed times t, that's a scalar multiplication here, plus the norm of v times t dot. Now also recall that n is t dot over the norm of t dot by definition, which means that t dot is the norm of t dot times n. We have then the following representation of the acceleration vector. It's the time rate of change of the speed times t plus the norm of v times the norm of t dot times the principal unit normal vector. And here we have it. This will be the tangential component of acceleration, and this will be the normal component of acceleration. That's what we call them. AT is, by definition, which means because I said so, the tangential component of acceleration, and AN is the normal component of acceleration. So the theorem is true, but these are really lousy formulas for the tangential and normal components of acceleration, and we can do better. First, let me point something out. The norm of acceleration squared is the acceleration dotted with the acceleration, of course, and that's going to be AT times t plus AN times n dotted with the same. We can FOIL this out. We will get AT squared times t dot t, and then ATAN times t dot n, and then another one of those, and then AN squared times n dot n. Now I want you to think about t dot p, t dot n, and n dot n. T and n are at a 90-degree angle to each other. They are orthogonal, and hence their dot product must be 0. On the other hand, the norm of t is 1, and that means t dot t is 1. The same is true for n dot n. We deduce then the following theorem. The norm of the acceleration vector squared is the tangential component squared plus the normal component squared. Remember, AT is a scalar and A sub n is also a scalar. This gives us a kind of Pythagorean identity for acceleration vectors. Kind of cool. It also shows that if you know the magnitude of the acceleration, then you do not have free choice on these two scalars. If you know one, you can figure out the other based on this equation alone. Also, you should notice that the normal component of acceleration by definition can't be negative. When you take the square root, you have to use the positive square root if you're solving for A sub n. Another interesting and important observation is that if the object is moving at a uniform speed, if the speed is not changing, then the acceleration is only in the direction of the normal vector, because the derivative of the norm of v would be 0. If you're at constant speed, the derivative of a constant is 0. If you do not move at constant speed, then you get a tangential component to acceleration. So the tangential component of acceleration is related to changing speed, either acceleration or deceleration. The normal component of acceleration is related to changing direction. So if you have an object that's changing direction, it will have a non-zero normal component. If the object is moving in a straight line, the normal component will be 0, and the acceleration will be all tangential, or no acceleration at all if it's moving in a straight line at constant speed. Once again, the tangential component of acceleration is related to changing speed. The normal component of acceleration is related to changing direction. Now, it would be nice to have simple formulas for the tangential and normal components of acceleration. So we're going to start with A equals AT times T plus AN times N, and I'm going to dot that with the velocity vector. When I do that, I'll get AT T dotted with V plus AN N dotted with V. Now the velocity vector, you will recall, is in the direction of the unit tangent vector. They are parallel. And that means N dot V is 0. Because N is orthogonal to T, it's also orthogonal to V. What is more, T is V over the norm of V. And we're dotting that with V. That gives us AT. V dot V is the norm of V squared. If we cancel and then solve for the tangential component of acceleration, we get the tangential component of acceleration is, I'll rewrite this as V dot A over the norm of V. Now this is a very simple formula to calculate. It just involves a dot product and a norm. It is less clear from this formula that the tangential component is related to changing speed, but it's easy to calculate. Now, how do you find the normal component of acceleration? Once again, we'll start with the representation of the acceleration vector as the tangential component times t plus the normal component times n. This time, we're going to calculate v cross a. Scalars pull out of this cross product. We'll get v cross t plus an v cross n. Now what? Note that v is parallel to t, and two vectors have a cross product equal to the zero vector if and only if they are parallel. So v cross t must be the zero vector. That leaves you with this v cross n. But keep in mind what that's equal to. We can think of that as the normal component times the norm of v times t cross n, where this norm of v can come out of the cross product. Now t cross n is the binormal by definition. If we now calculate the norm on both sides of the equation, these scalars come out of the norm in absolute value, but remember that an cannot be negative. So we get the norm of v times an. The norm of b, by design, is 1. We can solve this equation and find that the normal component of acceleration is v cross a in the norm divided by norm v. And that is very similar to the formula that we had for the tangential component. I want to write these two formulas down so that you'll have them together in your notes. They're very similar. They are both scalars. One error a lot of students make on the exam is leaving off the norm in the numerator for the normal component of acceleration. Don't do that. It's norms top and bottom. For the normal component, you use a cross product. For the tangential component, you use a dot product. It's fascinating these formulas are so similar. It makes them easy to memorize, seeing them together like this. For a simple example, let's suppose r of t is the parabola t squared. We'll assume that the third coordinate is 0, if you will. The velocity then is 1, 2t, comma 0, and the acceleration is 0, 2, 0. Note that I want to find the tangential and normal components of acceleration at t equals 1. So if t equals 1, right here, I want to find the tangential and normal components of acceleration at that point on the curve. Both of those are scalars, recall. Now, to do that, I need to find the velocity at t equals 1, which will be 1, 2, 0. The norm of the velocity is then the square root of 5. The acceleration is constant already. The acceleration at 1 is the same, 0, 2, 0. Let's calculate both the dot product and the cross product. So v at 1 dot a at 1 will be 4. And v at 1 cross a at 1 will be 0, 0, and then 2. The norm of v at 1 cross a at 1 will also be 2. It follows then that the tangential component of acceleration is 4 divided by the square root of 5. And the normal component of acceleration is 2 divided by the square root of 5. You can see that because at is positive, this curve is being swept at greater and greater speed at this point. It's accelerating in the direction of motion. It's also turning. Let's do another example. How about 2 cosine t to sine t, and let's do the square root of 5 times t. What kind of curve is this? It's a helix. Now the velocity. That's negative 2 sine, 2 cosine, square root of 5. The speed is going to be 4 sine squared plus 4 cosine squared, that's 4, plus 5, that's 9, square root. The speed is 3. The acceleration then is going to be minus 2 cosine minus 2 sine 0. The dot product at each point, you can see that we'll have a positive 4 sine cosine and a negative 4 sine cosine, that's 0, plus another 0. That's 0, which means the tangential component of acceleration is identically 0. It's 0 for all replacements of the variable t. And hence, this curve is being swept out at constant speed. It's a helix. It's just going around and around and around at a constant speed. Let's calculate v cross a. Let's see, we'll have 0 and then minus a negative 2 root 5 sine. 0 and a minus a negative is positive, but you have to switch the sign on the middle cofactor to root 5 cosine. And then a positive 4 sine squared and a minus a negative, that's still positive 4 cosine squared. That's just 4. What is the norm of v cross a? Well, you'll have 4 times 5, that's 20 sine squared, plus 20 cosine squared, that's 20, plus 16, that's 36. The square root of that is 6. It follows then that the normal component of acceleration is 6 divided by 3, or 2. I've finally come to the topic of curvature. We'll begin this topic in R2. Suppose we have some curve, and at some point we'll have a unit tangent vector t. If we draw in a line that's parallel to the x-axis, we'll define this angle off of the x-axis by the letter phi. There's the uppercase phi. These are phi. There's another version of phi that's sometimes written like this, but that looks too confusing with, but that may be confused with the notation for the empty set, sometimes drawn with a vertical bar through it to make it clearer. I'll advocate that you use this first version of phi on the left, because it's clearer. A curve has no curvature if phi remains constant. Objects that move in a straight line have no curvature. So how can we measure the curvature if the curve is not moving in a straight line? And it has to do with the rate of change of this angle phi. We can make the following definition. The curvature of some parameterized curve, r of t, is denoted by, sometimes with a kappa like this, or I'll just use k because it's easier for me to write, and defined by Now, there are actually two possible definitions. The curvature is the absolute value of d phi ds. You have to take the derivative with respect to a parameter that is geometrically significant. Otherwise, you could race through at different speeds or halting and taking off, and you can do a lot of different ways of parametrizing a curve. If you parameterize though with respect to arc length, that is of geometric importance. It gives you that you're moving at a constant speed. In fact, speed equal to 1 if you parameterize with respect to arc length. You take the absolute value. Now, an alternative definition would be that the curvature is just the derivative of phi with respect to s, without an absolute value. That way, if you're turning in a counterclockwise direction, you would have positive curvature. If you're turning in a clockwise direction, you would have negative curvature. You'll often see only the first definition given in textbooks, though the second definition can be useful. Now, there are some pluses and minuses for the definition of curvature that has just been given. First, it's restricted to R2. That's a problem. We need a more general definition eventually, but for now, let's continue to work in R2. Second, it doesn't give us a very easy formula for figuring out curvature. We need a better formula, but in its favor, it gives you a clear understanding of what curvature means. It's that rate of change of angle off of the positive x-axis, at least for curves in R2. So we need a better formula. Let's work on that. Let's suppose we have some curve, and here's our unit tangent vector. We'll draw in this horizontal with the angle phi. Note that the unit tangent vector has a horizontal and a vertical component, and because it has length 1, that means that t will have the following form. It is cosine phi sine phi. It must be. We'll have an x and a y. Y divided by 1 is sine phi, which means the y coordinate is sine phi. X divided by 1 is cosine phi. So again, x is cosine phi. Now, check this out. If we calculate the derivative of t with respect to arc length, the derivative of cosine phi with respect to arc length s will be negative sine phi times the derivative of phi. We must use the chain rule here. That's d phi ds, comma. And in the second coordinate, we'll have a positive d phi ds times the sine of phi. Note that we can factor d phi ds out, and we'll just end up with a minus sine phi, comma, cosine phi. The vector has norm 1. Scalars can come out of norms in absolute value. The absolute value of d phi ds is the curvature. So the curvature is the norm of the derivative of the unit tangent vector with respect to arc length. In R2, we have the following theorem. The curvature is the norm of the derivative of the unit tangent vector with respect to arc length. This is good because it now gives us a specific way of calculating the curvature, but it's kind of bad because the formula is still not a very easy one to figure out. There has to be a better way. There's another observation I would like you to make, and that is, for curves in Rn, we may make the following definition. The curvature is the norm of the derivative of the unit tangent vector with respect to arc length. We may now take this as a definition, and it works in arbitrary dimensions, not just in R2. So there has to be a better formula besides the one that we just had. Let's see if we can figure something out. Now, one problem is that I don't want to have to reparameterize with respect to arc length. Arc lengths are really hard to find. I want to avoid that if at all possible. So how about this? We parameterize with respect to whatever we want, and then use the chain rule. That seems like a much better idea. dt, the derivative of the unit tangent vector with respect to the parameter, an arbitrary parameter t, is a vector-valued quantity. What's next to it, dtds, is scalar. It can come out in absolute value. What's left over on the inside is just a t dot. Now, the dtds might look a little better if we flip it down. Now, I'd like you to recall that ds dt was the speed, the norm of the velocity vector, which means the absolute values are completely unnecessary, and we can rewrite this as the norm of t dot divided by the norm of v. Now you might remember that the normal component of acceleration was the norm of v times the norm of t dot. That means that the norm of t dot is the normal component of acceleration divided by the norm of v. From that, the curvature is the normal component of acceleration divided by the norm of the velocity squared. But remember, the normal component of acceleration was the norm of v cross a over the norm of v. We deduce then that the curvature is the norm of velocity cross acceleration divided by the norm of the velocity cubed. Let's call that a theorem. That looks like a very easy formula for calculating the curvature of a curve, and this works in R3. R3 because we're dealing with a cross product. If the curve is in R2, we can always extend it to R3 by adding a zero coordinate at the end. So it can also work in R2, but it does not work in R4 because of the cross product. I want to give you an example. Suppose r of t is capital R cosine t, capital R sine t, and 0. So we're dealing with a circle of radius r in the xy plane. The velocity vector is r negative r sine, r cosine 0, and the acceleration vector is negative r cosine minus r sine 0. The cross product then is 0, 0, positive r squared sine squared, minus a negative is positive r squared cosine squared. That's just r squared. It follows then that the norm of v cross a is r squared. The norm of v, scalars pull out in absolute value. It's r times the norm of minus sine cosine 0, which has norm 1. So the norm of v is just the radius r. It follows then that the curvature is r squared divided by r cubed, which is 1 over the radius. You should take note that the curvature of a circle is 1 divided by the radius. The smaller the circle is, the greater the curvature. The larger the circle is, the flatter it is, the lower the curvature. I want to go back for a moment and look at curvature in R2. In particular, note that the tangent vector is cosine phi sine phi. Suppose the curvature is a known function of S. It's just given. We know the curvature at every single point, and let's suppose that's all we know about the curve. If the curvature is d phi ds, the alternative definition that we've given, then we can calculate phi as follows. Phi of s minus phi of s naught is equal to the integral from s naught to s of the curvature, let's say d at x dx, just using a dummy variable x. It gets integrated out and we end up with a function of s after we evaluate the definite integral. You can see then that if you are given the curvature function, you can integrate that and find the angle up to some initial angle of rotation So you'll have to be given this initial angle of rotation in order to completely determine phi. But at least we will know phi up to some initial rotation. Next, that gives us the unit tangent vector. Recall that t is the derivative of position with respect to arc length. That's true because the norm of dr ds is the norm of dr dt dt ds. The norm of dr dt dt ds is the norm of this velocity vector. The scalar comes out, but that's ds dt, which is also the velocity vector in its norm, the speed, and so you get 1. Which means, since dr ds is dx ds dy ds, and we are able to construct phi up to an angle of rotation, we can construct this unit vector. That means dx ds is known as the cosine of phi of s, where we are able to construct this phi of s. To figure out the location x, all you have to do is integrate. I should use a different dummy variable until after we integrate. Cosine of phi of x dx. This gives us x and y up to some initial translation, x naught, y naught. What are the implications of this statement? Given the curvature as a function of arc length, we can find r of s. We can reconstruct the whole curve up to a translation x naught, y naught, and rotation through some angle phi naught. In other words, if you only know the curvature, one scalar valued function of arc length, you can reconstruct the whole damn curve up to a rigid motion, translation, and a rotation. We say that in R2, the curvature forms a complete set of invariants. If you know that one scalar valued function, you can reconstruct the whole curve. At least you'll know all of its geometry, because the geometry doesn't change through a rigid motion. I'll say that again. All of the geometry of a plane curve is completely determined by one scalar valued function, the curvature. Given the curvature, you can reconstruct the whole curve up to a rigid motion. In R3, it takes two scalar invariants to completely determine the curve, the curvature and the torsion. I want to first develop a specialized formula for the curvature for plane curves. Let's let our function be given by y equals f of x. Then we can form a parameterization, x, f of x. And that gives us a velocity vector, 1 f prime of x, and the acceleration is 0 f prime prime of x. The cross product then, if we extend this by adding a 0, will be 0, 0, and then f prime prime of x. It follows then that the norm of v cross a is the absolute value of f prime prime of x. The norm of the velocity is the square root of 1 plus f prime of x squared, so that the curvature, and here's the formula we're trying to derive, is the absolute value of f prime prime over 1 plus f prime squared to the power of 3/2. Here we have a power of 1/2. We have to cube that, the norm of v cubed, in order to construct the curvature. Let's suppose that y equals x squared. Then y prime is 2x, and y prime prime is 2. It follows then that the curvature is the absolute value of 2 over 1 plus, well, 2x squared to the power of 3/2. You can see that when x is equal to 0, we'll have a curvature equal to 2. As x tends to infinity, the curvature goes to 0. Which makes sense, because for a parabola, you get less and less curvature as you go out. The highest curvature is at x equals 0. I would now like to derive the formulas of Frenet. It's related to torsion, as you'll see. A Frenet frame is the T in B frame. And I want to look at the derivatives of these things. First of all, note that T dot T is 1, because that's the norm of T squared. If we take the derivative with respect to arc length on both sides, on the right-hand side, we have to use a Leibniz rule, a product rule. That's going to be the derivative of t with respect to s dot t plus t p dot the derivative of t with respect to s. Since the dot product is symmetric, we get twice t dot dt ds. Since we get 0 on this side, that means t is orthogonal to dt ds. That means wherever dt ds lies, it's in the plane orthogonal to the unit tangent vector t. It has to lie only in the direction containing n and b. Whatever dt ds is, it has to have some component in the direction of n and perhaps some component in the direction of the binormal b. Now, but we know better. We know the normal vector is t dot over the norm of t dot. What is more, this allows us to use any parameter we want. Let's use the arc length parameter. This tells us then that dt ds is a scalar times n. This scalar, you'll recall, is the curvature by definition. dt ds is the curvature times the principal unit normal vector n. This is one of the three Frenet formulas. The Frenet formulas describe how the orthonormal frame, the TNB frame, the Frenet frame, moves, changes, as you move along the curve. This gives you a rate of change on that unit tangent vector. So far, the rate of change of the unit tangent vector with respect to arc length is the curvature times the principal unit normal. I'll put that over here. Now let's look at the fact that n dot n is 1, because again, n is a unit vector. If we take the derivative on both sides, the derivative on the left is 0. The derivative on the right is 2 times n dot dn ds. This tells us that n is orthogonal to dn ds, and therefore dn ds looks like some scalar valued function times the unit tangent vector plus some scalar times the binormal. It has no part in the direction of the principal unit normal vector n. Now, we need to figure out what a and b are. Actually, we're going to define what b is in a minute. But in terms of a, we can figure that one out. We'll use the fact that 0 is t dot n. If we take the derivative on both sides here, the derivative of 0 is 0. On the right-hand side, we have to use a Leibniz rule. dt ds dot n plus t dot dn ds. We already know that dt ds is the curvature times n, and we're dotting that with n. Here we have t dotted with dn ds, and we know that is at plus b times the binormal b. When we dot t with b, we get 0 because t and b are orthogonal. T dot t is 1. N dot n is also 1. This equation tells us then that the constant a is minus the curvature. We will make the following definition. B is the torsion, which is denoted by tau. We'll have to figure out a formula for finding it. So far, we know the following. We have the second formula of Frenet. How does the principal unit normal change as you move along the curve? Minus the curvature times the unit tangent vector plus the torsion times the binormal. This is our second formula of Frenet. There's one more. How does the binormal change? We've played this game a couple times already. We'll play the game again. One is b dot b because b is a unit vector. We'll take the derivative and get twice b dotted with the derivative of b with respect to s, which means that b is orthogonal to dBds. So whatever dBds is, it has to be a scalar times t plus another scalar times n. We just have to figure out what these two scalars are. Now 0 is t dot b because they're orthogonal. That means taking the derivative and applying a Leibniz rule, dTds dot b plus t dot dBds equals 0. dTds is the curvature times n, according to the first Frenet formula, and if we dot n and b, we must in fact get 0. So we get t dotted with at plus bn. When we dot t with n, we get 0, and t dot t is 1. So we get a. A is 0. That leaves only one scalar to find, and that is the coefficient of n in the formula for dBds. There's only one more play to make in this game, and that is to note that when you dot n and b, you get 0. Taking the derivative, we get dnds dot b plus n dot dBds. We know what dnds is. It's right above here. We get from this formula that 0 is, let's see, dnds is minus curvature times t plus torsion times b dotted with b plus n dot dBds is b times n. Now, when we dot t and b, we get 0 because t and b are orthogonal. When we dot b with b, we get 1 because b has length 1. That leaves us with tau. And then over on the last term, n dot n is 1. We'll have left over a b. It follows then that b is minus the torsion. That gives us the final formula of Frenet. I'll write these out all together. So, I'm going to write the formulas of Frenet. I'm going to have a t column, an n column, and a b column. First, dTds is the curvature times n. dnds is minus the curvature times t plus tau times b. And dBds is minus tau times n. This gives us all of the formulas of Frenet in a form that is easy to remember. The thing to point out here is that t is dx ds, dy ds, dz ds. If you can figure out the unit tangent vector, then you can integrate to find the position vector xyz. But the unit tangent vector has a rate of change that depends upon n, N has a rate of change that depends upon t and b has a rate of change that depends upon n. You have to know the curvature and the torsion in order to solve this linear system of differential equations. There is an existence theory for the solution to these forms of systems of differential equations that is usually presented in a course on differential equations. It has an existence and uniqueness theorem. If you know the curvature and the torsion as functions of arc length, it's possible to solve the system of differential equations for the vectors t, n, and b to find a suitable method of integration so that you can get rid of all of these derivatives. And if you can get rid of the derivatives on t, n, and b, then in particular you can find t and integrate that to reconstruct the curve up to a constant of integration which represents a rigid motion. So once again, curves in R3, space curves, have a complete set of invariants consisting of the curvature and the torsion. If you know the curvature and torsion, you can reconstruct the entire curve up to a rigid motion. You will have all of the geometry of the curve encoded in the curvature and the torsion. The only thing that we haven't done to this point is find a suitable formula for the torsion. We have a formula for the curvature. I want to find an efficient method to calculate the torsion, tau. First, recall that dnds is minus curvature t plus tau times the binormal b, which means that if we calculate dnds dot b, b dot t is 0, b dot b is 1, that gives you the torsion. Also, note that b can be found as follows. We can take v cross a if v lies in the direction of the unit tangent vector t. The acceleration lies in the plane containing t and n. The cross product has to be normal to the plane containing t and n. It has to be normal to both, which means it has to be in the direction of b up to, it may not have magnitude 1, so we have to normalize. So an easy formula for b is v cross a over the norm of v cross a. Now keep in mind that the acceleration vector is the tangential component times t plus the normal component times n. It follows that the rate of change of acceleration with respect to arc length is, I guess we better use some product rules here. The derivative of the tangential component with respect to arc length times t plus at times dt ds, which we know is the curvature times the normal vector, plus the derivative of an ds times n plus an times the derivative of n with respect to s. What happens if we dot the rate of change of acceleration with respect to arc length with the binormal b? The tangent vector, unit tangent vector t dotted with b is 0. dt ds lies in the direction of the principal unit normal vector, and that too is orthogonal to the binormal b. The third term in the sum is also orthogonal to b, and that leaves only an times dn ds. We get an, according to the formula for Frenet, dn ds is minus curvature times t plus torsion times b, and we're dotting with b. T dot b is 0, we end up with the normal component of acceleration times the torsion times 1. B dot B is 1. We have then the torsion is the derivative of acceleration with respect to arc length dotted with the binormal divided by the normal component of acceleration. Before proceeding with this computation, I want to note that the rate of change of acceleration with respect to arc length is equal to the rate of change of acceleration with respect to any parameter times dt ds using the chain rule. That's going to be the rate of change of acceleration with respect to, say, time. That's called the jerk. This dt ds is 1 over ds dt, which is the norm of the velocity. So we end up with the derivative of the acceleration divided by the norm of the velocity vector. We have then 1 over the norm of the velocity vector times the jerk, the derivative of the acceleration, dotted with the binormal. The binormal, you'll remember, is v cross a divided by the norm of v cross a. And that's all over the normal component of acceleration, which we had a formula for. The norm of v cross a over the norm of v. What does this all reduce to? These norm of v's cancel. We get the torsion is the jerk dotted with v cross a over the norm of v cross a squared. The torsion is thought of as the tendency of a curve to leave a plane. If the torsion is identically zero, then the binormal is identically constant, and you have the curve only living in the plane containing t and n. Let's do an example. Let's suppose r is, let's say, a cosine a sine b t. And the velocity is minus a sine a cosine b. And the acceleration is minus a cosine minus a sine 0. And the jerk is going to be a sine minus a cosine 0. V cross a is going to be, let's see, we get 0 and then minus a negative. We get AB sine. 0 and then minus a negative, but you have to put a negative on the middle cofactor. AB cosine. Positive a squared sine squared. Positive a squared cosine squared. You just get the constant a squared. Note that a as a scalar can be factored out of this vector. It follows then that the norm of v cross a is, we'll assume a and b are both positive. A comes out of the norm in absolute value. You'll have b squared sine squared plus b squared cosine squared, that adds up to b squared, plus a squared square root. The jerk dotted with v cross a is, we have a scalar a, we'll have ab sine squared plus ab cosine squared, that's ab, plus 0. It follows then that the torsion is a squared b divided by a squared times a squared plus b squared. the norm of v cross a squared. You have then b over the quantity a squared plus b squared. And that gives you the torsion for this helix. Note that if b is equal to 0, then it's just a circle lying in the xy plane, and the torsion is identically 0 in that case. Also, as b tends to infinity, the torsion tends to 0, because as b tends to infinity, the curve stretches like a stretched spring in the vertical direction, taking off very fast in the vertical direction. And if the curve is just a straight line in the limit as b goes to infinity, again, both curvature and torsion should be 0 in that limit.